Right. Okay. Let's get going. What I would like to do today is finish the two remaining examples in the current chapters, chapter 3. Before we go to that, 50 minutes is all I asked for. 50 minutes. Right, so just before we go and solve the two remaining cases I have in that chapter, so I went online and found few of the many different cases where we use beams. So some of you are doing civil engineering, some are doing mechanical, but these are mostly from civil engineering part. So I'm sure you've seen structures like that, a beam within a civil engineering structure there to provide support, and it's been supported by pin connection at the end. So that is going to take some load. And what we are trying to do last week and also this week is once the loads are basically put on that beam, you want to make sure that the magnitude of the stress that is developed is not too high, that it will break the beam. And you don't want the beam to actually have a very large deflection. And that, I'm sure you've seen that. You first had a standard structure like that. So it's more like a simple table. So you can see the beams running across like that. So and you put weight on it, and you don't want the beam to also break or also to have larger deflection. And you can see all the vertical supports. So our next chapter, the next topic, we'll be looking at that. So those ones. What is the maximum compressive load you can put on that? So that we'll be doing that from next week. And here are two examples of a simple cantilever structure. That one without a load, and that is a part of a building. You can see that section that is just free at the end. Once anybody goes into that section, you'll be putting weight on that. You want to make sure that that structure is able to take the load. And so common one is a bridge. So that is simple support. And what happened in between the two supports is what we are doing. We are doing here. So you want to make sure that it doesn't deflect too much, and you also want to make sure that the stress is not too high. So those vertical supports, we'll be looking at that next week to look at what is the maximum support load you can put on them, and that is very similar to this as well. So the beams are the one that runs along here, and the supports are this one. So next week we will look at the supports, and today we're going to finish up on the beams. So you can find so many different cases like that. So let's go back to the section. So example 3.2. So we want to look at the deflection of the beam. So we've already talked in terms of how we look at the magnitude of the stress. So here we are interested in the magnitude of the deflection. So we are here going to assume that we will know. So we will know the value of the force, the length, the Young's modulus of the material from which it is made, and the second moment of area of the cross section of the beam. So those one will have some numbers. But so this one we're going to do without any numbers, and the next example I will have some numbers in it. So we are interested in finding the deflection and the slope. So what we want to find deflection and slope, where F is applied. So we know how the beam is going to deflect. We know it's going to deflect downwards where that force is. So we want to find what is the magnitude of that to make sure that it is within the level that we want it to be. Who is that? Whoever it is, just talk to me. Don't talk to your friend. I'm here to listen. Right, so let's start. So because we are interested in deflection, our starting equation is the beam deflection equation, d2v dx squared equals minus bending moment m all over ei. So that's what, so now we want to find what is v at any location along the length of the beam, and then we can now find the magnitude where the force is. V is the magnitude of the deflection going downwards, and x is the distance from our reference. Our reference is always from the left, and m is the bending moment at any point. So we know that our bending moment m will be a function of where you are along the beam. So where x is starting from here. So let's say that is x. So bending moment will depend on where you are along the beam, which we're going to show soon. It will depend on the force that we have on that beam, and will depend on the length of that beam. So let's go through how we find the bending moment for a simple cantilever, which is like that. So I'm going to start now and draw my free body diagram. So I'm going to just take any distance x. So the way we do it, that we say you take any distance x from the load. So that is any arbitrary distance x. So we make a cut. We put aside what is on the right. We look at what is on the left. So if we were to do that, so I will have f, and I have my distance x, which is like that. And we want to find what is the bending moment on that surface. So that is no more in equilibrium, because we've removed some part of the beam. In order to make sure that it is in equilibrium, you must have a shear force to balance it off. You must have a moment to balance that off. It is that moment that we're interested in. We're not interested in the shear force. So here, it's only the magnitude of the bending moment that we are interested in. If we take moment about that plane, what we'll have is that m plus fx will be 0. So f times the distance from that plane. So our bending moment, therefore, at any distance x from the left-hand side will be minus f times x. So remember our sign convention for positive and negative bending moment. So because that is negative, if you recall what we said, that anything that leads to that is positive. If it is doing that, and that is negative. And it is clear from that beam that because you are applying the force on the top, it's going to bend downwards. It's going to go this way. So that's why we have a negative sign there. Now let's apply this. So we're now going to put our m, which we now know at any distance x, into that equation. We can do the first integration and the second one, and then we'll be able to find the magnitude of the deflection. So now I'm going to substitute my bending moment, which I know, so which will be the same from the beginning to the end of the beam, because there is no other load applied apart from load F. So let's put that there. So I will now have d2v dx squared, which equals minus m all over ei, is now, so instead of minus m, I now have minus fx, so I have minus 1 over ei. My f is minus fx. That's that. Now I'm going to do the first integration, and I'm going to do the second one.
Excuse me.
Yeah.
You got the answer minus fx because we assume that this is the anti-clockwise direction. So can we just...
No, I'm not using the phrase clockwise or anti-clockwise for bending moment. I'm looking at whether the moment is going to give me this or it's going to give me that.
But see, the drawing in the middle, right?
Which one? This one?
Yeah. So
Yeah.
you've got M
Yep.
and the anti-clockwise arrow, right?
Which anti-clockwise arrow? This one?
Yes.
Yeah.
And your answer is negative. So we know that we assume the direction is was wrong. If the answer was positive, that we knew that the answer was
Yeah.
direction is positive.
Yeah. So this direction I've chosen as giving me this. But because I'm getting a negative number, it means that this moment here is actually acting in the opposite direction.
Yeah, so can we just substitute fx instead of minus fx if we like take this into consideration, that we assume the direction is wrong, the one that we chose?
You mean, so in your free body diagram, if you chose this to be going the opposite direction?
Yes.
Yeah. So if you are to do that, you will get a positive value here. Yeah.
And then can I just substitute that into the second equation for the differentiation?
Yeah. You will see when we do that. You will end up with the same thing. Okay. So if we were to do the first integration, so you have minus, I can just get rid of that. So that becomes 1 all over EI multiplied by that. So if you do the first integration, so we will have dv dx equals 1 over EI f x squared over 2. So plus some constant which we don't know. And then we do it again. We have a second one. I will have 1 over EI f x cubed over 6 plus C1x plus C2. Remember, we want to find the magnitude of the deflection. We want to find the magnitude of the deflection at any distance x from the left-hand side along the length of the beam. So that is the first integration. That is the second one. And then we've got that. Now we want to find what those two constants are. So we go back to the beam and we look at what type of support we've got. Is there anywhere in the support where we know the deflection? Anywhere in the beam where we know the rotation, which is dv dx. So if I just show the beam, which I think I'll be able to show here. So if my x is 0 here, starting from here, going towards the right. So is there anywhere in the beam where we know what the deflection is? Sorry? Where is 0? Okay, is that right? Well, not exactly, because where x equals 0 is where your load is. That's what we are trying to find. We don't know that. That would depend on the magnitude of the load. Okay? But one thing we know is this support. That is fixed. The beam cannot deflect at that location because it is fixed there. And it cannot rotate at that location because it is fixed there. So when x equals L, the deflection V has to be 0. When x equals L, the rotation, which is dv dx, has to be 0 because that support is what is called built-in support. No deflection, no rotation. And those are the two main conditions that we need. And we will use that to find those two, C1 and C2. So we'll say put out your boundary condition. That is what you know at the boundaries. So at x equals L, V equals 0. And we'll say at x equals L, dv dx equals 0. Because there is no rotation and there's no deflection at that support. So if we start with the one with dv dx first, okay? So if I put x equals 0 there, I'm going to say dv dx at x equals L equals 0, and I'm going to put x equals L in that equation. I'm going to have 1 over EI f L squared over 2 plus C1. Yep. So then I can find C1. All we've done, we just made instead of x squared, we have now what x is, x equals L. So what that then means, therefore, is that our C1 equals minus FL squared all over 2 EI. Hope that's clear to everyone. And then we go back and we do it for the second one. I will say, okay, what's happened when we put x equals L and v equals 0 at that point. So we use that here. Now I know C1, so instead of C1 here, I'm going to use this. So I'm going to move that up and do that. So we go and write. So v equals fx cubed over 6ei plus c1x plus c2. So let's do that. So at we say v at x equals L equals 0. So that's all I need. So I'm going to put that in and put the value of C1, which we now know. So we do that and we'll say we now have FL cubed all over 6 EI minus FL cubed all over 2 EI plus C2. So we substituted x equals L. We substituted the value of C1, which we now know. We can now find C2. So I will now give what that is. So you can work that out. So C2 will be FL cubed all over 3 EI. So I know C1, I know C2. I can put that back into my equation now. I can now determine the magnitude of the deflection, of the rotation at any point along the length of the beam. So we put that back. So if you put that back into the two expressions for the slope and the vertical deflection, we'll be able to show, to find what V is. So we now have the deflection V, which is positive downwards, will be F all over 6 EI x cubed 3L squared x plus 2L cubed. Okay. And dV dx, which is the slope, is F all over 6 EI 3x squared minus 3L squared.
So you move the page down a bit.
Sorry?
You move the page down a bit.
Right, so now we have that. So the question is, what is the magnitude of the vertical deflection where the load is applied, and what is the slope where the load is applied? Now, now we go back and we'll ask ourselves, what is the value of x at that point? So the load, our reference is to start the x from the left-hand side, which is where the load is. So where the load is applied, my x is 0, and therefore I can put x equals 0, and it will tell me what is the magnitude of the movement of the beam where the load is applied. So if you want to do that, so I can now say that deflection where F is applied will be V at x equals 0, and we just we put x equals 0 there, and we'll be able to show that that is just 2L cubed multiplied by F all over 6 EI, and that is FL cubed all over 3 EI. So if I know the load, and I know the length of the beam, and I know the modulus, and I know the second moment of area I can find the value of the deflection. So I will repeat again. So I will say here, be consistent with unit. So be consistent with you. What that means is that if your length is in meters, your force is in Newton, for example, your Young's modulus must be in Newton per meter squared, and your I, second moment of area, has to be in meter raised to power 4. Okay, so So if that deflection is, once you put that in, if it is positive, it means that the beam has been deflected downwards. If it turns out to be negative, it means that the beam has been deflected upwards, because our positive direction is going down. And the slope is the same, so you can put x equals 0 here. You'll be able to find the slope. And if the slope is a positive number, what that means is that the tangent to the deflection is like that. If that is like that, so that is positive slope. If the tangent to the deflection is like that, then that is negative slope. So if you go from your x and you have to go in the anti-clockwise direction to get to the tangent, then that would be a negative slope. So, okay, so is that clear? I'm going to do the next one. The next one is a bit long, and there's a reason for that. So,
And what if we choose that x equals 0? Because this is where the load is applied, right?
no, there's no where the load is applied. I've said that many times. Our convention is to start from the left and walk to the right.
Yeah, and f where x equals 0, this is where the load is applied.
Yeah. It just happened that for this one,
Yeah, for this one.
for f is there, but for your x you always start from the left, going to the right.
But if the load was in the middle, would we have to go over exactly the same procedure?
Correct.
From the left or from the middle?
No, you always go from the left towards the right. Sometimes you can start from your support. Okay, in this case, our support is on the right hand side. Okay, so, but if you want to start from the right hand side and walk back to the left, you can do that, but just be careful with your signs.
Yeah, but I'm choosing this on the boundaries. I can't choose it in the middle, right?
No.
If the load is applied in the middle,
Yeah.
I still have to choose the left or right side.
Yeah. You will say in the next one where we have two loads, for example. So let's go through the next, which is a bit long.
Sir, see the differentiation you got?
Yeah.
How did you get 3L squared?
Which one?
The one in the middle on the page just now?
This one?
Yeah.
This one? No, that is V. That's not a differentiation. Or is this one you're referring to?
Yeah.
All we've done, we've just differentiated this. If you differentiate x cubed, you get 3x squared.
Yeah.
If you differentiate 3L squared times x, you get 3L squared. If you differentiate 2L cubed, L is a constant.
I'm seeing it now.
Yeah, okay. Right, so let's do the next one, which is a bit long. So, and there's a reason for that because of the nature of the beam. So now we have a simply supported beam with two types of load. One is UDL, uniformly distributed loads, and the section which is an overhang, as it is normally referred to, has got a point load. Now, so it's the same thing. We want to find what is the magnitude of the deflection at any point along the length of the beam, and what is the magnitude of the rotation at any point along the length of the beam. Usually, we're interested in the magnitude of the maximum deflection and the maximum rotation. That's what we want. So maybe I should emphasize, if I go back here, you might see here that our deflection depends on EI. So if I want to reduce the magnitude of the deflection without changing the load, if I want to make that very small without changing the load, I have an option to either reduce the length or increase the modulus or increase I. So you can change the magnitude of the deflection without reducing the load. We can reduce the length, increase the modulus, or increase I. To increase I, you have to change the size of the whatever cross section that you are using. So let's go back to this. So I'm going to start. Here it's the same thing. We want to find deflection. I'm going to put some numbers in. Hopefully we'll be able to finish this before today. So let's just assume that our P here is 20 kilonewton. Okay. Let's assume that our Q is 30 kilonewton meters. Okay. And our A, which is the length between the support, is 4 meters. And the overhang is 1 meter. Modulus is 200 GPa, that is gigapascal. And I is 4 times 10 to the power minus 6 meter 4, like that. So let's assume that's what we got. Now we have some numbers. But so we will go through the solution without numbers, and then we'll put the numbers in right at the end. So I know that the deflection which I want, dV, the 2V dx squared is minus m all over EI. So that's my starting point. But I cannot use that unless I know what the bending moment is along the length of the beam. So that's the starting point. So we want to find what the bending moment is. And we've done this a few times now. So we're going to start first, find the reaction. Because we have two simple supports, we want to find the reaction forces. And from there, we can find the equation for the bending moment. And the bending moment equation we need two of them because the loading on this section of the beam is not the same as the loading on this section of the beam. So we need the bending moment equation for section AB, and we need another one for section BC. So let's find the magnitude of the reaction forces. So for the reaction forces, we need our free body diagram. So if I just draw that, so I have reaction force at A, I have reaction force at B, I have a point load P that is applied, and we have a UDL which is going to act through the middle. I'm going to call that there. So I'm going to put this now, no number, just Q times A, because that is the total net down force that is acting. Q is load per unit length, and then the length over which it acts is A. The net effect is to act through the center. So our A is this, our B is this, and what is this length here? So A over 2, thank you. So that is A over 2. So if you like, you can put your, because we have the numbers, you can put your numbers in. But it gets a bit messy as you go along. The best thing is to just do it without numbers, and then at the end, and then you then put it in. So let's do that. So everybody should be able to find the magnitude of the reaction forces. We're going to start and say summation F equals 0. That is total force acting downwards must equal total force acting upwards. So that's what that is. So what we have is RA plus RB must equal P plus QA. Yeah, so that's the first one. And the second one is to take moment. I'm going to take moment about A. So you can take your moment about any point. So moment about A equals 0. I want to take moment about A. So for all the forces. So if we are to do that, so I have RB will have a moment of A times RB acting in the anti-clockwise direction about A. And the second moment is the one due to P, and that will be acting in the opposite direction. That is P times A plus B. And the other one is Q minus QA multiplied by A over 2 equals 0.
Could you state the direction of the bending moment you chose?
Which one?
Like NA equals something, and you're operating with different signs.
Yeah, so so this one is
State which direction you chose.
yeah.
That's okay.
Yeah. So but is it it doesn't matter which direction you shoot, whether you shoot it that way.
So,
So,
that later,
yeah.
'cause I'm confused.
so now you can solve that. So I'm not going to go through how to solve that. I think everybody should be able to solve that. So we need to find RA and RB in terms of P, in terms of Q, in terms of A, and in terms of B. So if you were to do that, so we will end up with RB equals QA over 2 plus PL over A. Okay. So remember, we know Q, we know A, we know the length. So when I say L there, so let me put that. So L is A plus B. So that is the total length of the beam. So we know all of that. So this will just be a number. Okay. So now you can put the value of your load in, which I'm going to do shortly. And our RA will be QA over 2 minus P times B over A. So if you put the numbers in, which is value of Q, value of A, value of P, then we will get RA of about 55 kilonewton, and we get RB of about 85 kilonewton. Okay. So now we have that, but our aim is to find the magnitude of the deflection. So I need to now go back and now ask myself, what is the bending moment? So anywhere along the length of the beam. So we go back again. We now start to find what is the bending moment equation. So like I said, there will be two bending moment equations. One for the section AB, where we have the uniformly distributed load, and for section BC, which is at the second end of the beam. Okay, so let's now do how to find the bending moment now that we have the reaction forces. Now we want to find the bending moment. I'm going to start with section AB first. So section AB is the one that has the uniformly distributed load. So we're going to take any arbitrary distance from the left-hand side, but we are still within that section AB. So I'm going to draw my free body diagram of the beam at any arbitrary distance, x. This is my RA at the end. My x is up to there. I have my uniformly distributed load acting on that section, which is Q. We will have a shear force. We will have a bending moment M. So M is the one that we want to find. So that's my free body diagram. You should always draw your free body diagrams because we are looking at section AB. So here our X has to be from, let me show the diagram again. So I want you to tell me what is the limit of X in that. So what is the limit of X?
4 meters.
Sorry?
4 meters.
4 meters. So we'll go X, we only have a value between 0 and A. A in this case is 4 meters. Okay. So let's write down the bending moment equation. So we've done this few times now. So I'm going to write my bending moment equation, and I'm going to say I've got M acted that way, and then I have RA multiplied by X, and I have Q multiplied by X, and then multiplied by X squared over 2. So I have not put any sign here. So what should that sign be? I've left that intentionally to let somebody tell me.
Positive.
Positive? Yeah? Positive, great. So yeah, we've got that. So now we can write down it's M that we want. I will now say M equals RAX plus, sorry, that should be Q just X over 2, QX squared over 2. So now I can now put that back into my the relationship between deflection and bending moment. But because I know RA and I know Q, okay, I can put them in to make life a bit easier. So we know RA is 50.
Negative then, no.
Sorry?
Is it minus QX?
Oh, sorry. Thank you. Yeah. So we know RA is 55 kilonewton, and we know that Q is 30 kilonewton meters. So I'm going to put those in. And I'm going to say again, be mindful of units. I'm going to put them in as kilonewtons. Okay, and we can use that much later on. So I'll put them in, and I'll find out that M is 55x minus 15x squared, where x is in meters and M in kilonewton meters. Okay, so because we put our load in as kilonewton, so the moment must be in kilonewton meters. So now I can put that into my moment deflection equation. But before I do that, I want to write down what is the bending moment equation for the second part. Okay, so that we finish with finding all the expression for the what is the bending moment. So we know the first one. So bending moment M equals 55x minus 15x squared, x between 0 and 4 meters. Now we want to do what is M between 4 meters and 5 meters, which is the end of the beam. And then we can go and find what the value of the deflection is. So if we go to the second part, which is section BC, then we do again, we draw our free body diagram. Now, the section we are taking is now beyond the support B. So we now have, I now have that. I have my RA here. I have my RB acting there. And I have my distance X, which is all the way to there. So my distance X is any point between B and C. So the limit of X in this case will go from 4 meters to 5 meters because we are looking at section BC. So my uniformly distributed load is acting over all of here up to there.
So you mean, is it from 4 or from 0 meters then?
Sorry?
Shouldn't it be 0 meters then?
Which one? This one?
Yeah.
No. Because we are, your reference is always on the left. If I go to the beam again, your reference is here,
Yeah.
but we are only interested in what happened between here and here. So when you are here, and you are starting from this point, so my X is A at this point, which is 4. So we are only interested in section BC.
So why did we write the body diagram for all the section, like all the section from A to C?
Because you take your section going from left to wherever you want, and you remove whatever is on the right-hand side. Okay, so now we want to put what is active. We always have shear force. We have a bending moment, which is the one that we want to find. So the uniformly distributed load, which is acting over that section here, which is our A, which is 4 meters, the effect is to have a net effect of acting through the center of QA, right through the center. So when we take the moment, we have to consider that as well. So let's now write our moment equation. So that bending moment M, I would say plus QA, which is the force acting through the center there. What do I multiply that with? We are taking moment about here. How far is that force QA from that particular cross section? A plus X minus B.
X negative 2.
Yes. So this distance here is X. That distance there is A over 2. So what we want is, what is the distance? What is this one? That would be X minus A over 2. So I multiply that, I will say I've got X minus A over 2. Yep. Is that clear? And then I go to the next force. The next force is RB. We have RB. Yeah.
Since we know B is, like this distance, B is 1 meter.
Yeah.
Can we say QA plus QA multiplied?
So we are not where B, we are not where,
If we took the center point for us, we didn't start from A, we started from B.
yeah, no.
If we start working from the right
You-
number.
Because if you start from here,
No, I mean, if I would work here all of it,
Yeah.
I didn't start from the left, I started from the right.
okay. So if you are starting, if your reference is here,
Yeah.
if your reference is here, you'll be taking moment at any distance from that point. So when you are up to here, it's only P that will have effect on the bending moment here. Once you go here, your P and the reaction force here and this one here will have an effect. So you need to consider all the loads. So it doesn't matter where you start from, but make sure you do not miss out all the loads acting on the beam. Just,
Yeah, I got it.
okay. Now, so I put my reaction force RB there. What should I need to multiply that with to find the moment about there?
X minus A.
X minus A. That's correct. We multiply by X minus A. Is that a plus or is that a minus?
Minus?
Because QA is right now, and we have to calculate.
Correct. So that is minus. So is there anything else we've missed?
How is it minus, please?
Yeah, just give me a minute. I'll come back to that. So one person at a time. One person at a time. Right. I'll come back. So, is there anything we've missed? And then I'll come back and explain that to you. Okay. RA. Like that's what I said. So you must make sure you consider all forces acting. So we now to look at RA, and what should we do there? Is that RA multiplied by what? Multiplied by X. Is that plus or minus? Minus. And that is 0. Now we've taken all. Right, so to answer your question, we are taking moment about here. So, and you are looking at every single force that you have on the beam, and you are finding out what is the moment of that force about that section there. And the moment is the force multiplied by the distance from where you are taking the moment at. So, but just beware of your sign. So here we've assumed that this is our positive direction, and any moment that is not in this direction has to be minus. And that's what we've got. Now I can write down that moment equation there. If you are to do that, remember we know RA, we know Q, we know A, so we know everything apart from that variable X. So I can write down the moment M equals RAX plus RBX minus RBA minus QAX plus QA squared over 2. So all I've done, I've just brought all these terms to the other side and open up whatever brackets that we've got. Now I can put in all the values. So we know Q, we know RA, we know RB. So I'll say, so let's just say, but RA equals 55 kilonewton, RB equals 85 kilonewton, and A equals 4 meters, and Q equals 30 kilonewton meters. So if you put all that in, we will get a simple expression for M to be 20x minus 100. So, and our x now, because we are starting from the left, has got a minimum value of 4 meters and maximum value of 5 meters. So x here is in meters and M in kilonewton meters. Okay. Because we put in the forces as kilonewton. Now I've got the bending moment equation for the two sections. Now I can now go back and do my double integration and then put in my boundary conditions there. So I don't think I've got enough time. I'm going to just stop this one here because the next stage is a bit long for the first integration, second integration for the two parts, and then we then use that. So I will finish this one off on Monday, and then we will start a new topic on Monday. You should now be able to do everything in paper 1 and paper 2 of the tutorials. Now, no excuses, please. Get it done. Get it done. Time is going. Guys, if you want to ask any question, 4 o'clock today, I will be in my office waiting for everybody to come in and come and ask anything you want to ask.
Can I ask one question now? That's okay.